All right, so as I was saying a second ago, guys, last year, 2 of the free response questions had some piece of this in them, and that was the first. Really had never been anything like that before. So what we're going to do is work this problem. Make sure that you know how to do this stuff, because it's actually not hard. It's just you got to know what you're doing. So let me get a copy of the question so I can switch slides. But when you're doing this kind of thing, well, before we do that, we've got an experiment. We're essentially measuring what's the effect of different amounts of fertilizer on plant height. So what's our independent variable in this experiment? What's our independent variable? Fertilizer, right? It's the thing that you're testing. And because you change the amount of fertilizer, what changed? The plant height. It's the dependent variable. So keep that in mind. We're looking at 2 different concentrations of fertilizer, 20 and 40 grams per liter. We measured 4 plants grown at each concentration. So these are our samples, right? This is sample 1, sample 2. When you're doing this kind of statistics stuff, you pretty much always need to calculate what first? Calculate the mean. And everybody in here I know can calculate the mean. You just add them up and divide by the sample size, right? So for the 20 grams per liter sample, let's go 18 plus 22 plus 20 plus 26, and let's divide that by 4. So for that sample, we get 21 and a half. All right, for sample 2, we'll do the same thing. 32 plus 24 plus 29 plus 23. Divide by 4. We get 27 for our mean here. And remember, X bar is the symbol for mean. Next, we're going to need to calculate the standard deviation, because the standard deviation is part of the equation for standard error, right? We've got to know standard deviation before we can get standard error. So let's go to a slide where we have a little room to work. Let's work just on the 20 grams per liter sample first, remembering that our mean for that group was 21 and a half centimeters. Trying to get standard deviation. Remember that the equation for standard deviation is the square root of xi. Remember, what's xi stand for? What is xi? It's each data point, right? Each individual reading minus the mean squared all over sample size minus 1. So that's our standard deviation equation. So before we can do that, we need to make a little table. And our table will be xi minus x bar, and what's our other column? Xi minus x bar all squared, right? So we first of all going to write down our individual data points. For the 20 gram per liter sample, our points were 18, 22, 20, and 26. Those were our data points. So then we're going to subtract the mean from each one of those. So we're going to go 18 minus 21.5. Get negative 3.5. 22 minus 21.5. Get half, 0.5. 20 minus 21.5, get negative 1.5. And 26 minus 21.5, and get 4.5. All right, then we need to square each one of those. So 3.5 squared, 0.5 squared, negative 1.5 squared, and 4.5 squared. Everybody with me up to this point? So according to our standard deviation equation, what do we need to do next? Yeah, sum up that last column of our table, right? So we add up all those numbers there at the end. 20.25 plus 2.25 plus 0.25 plus 12.25. Now I'm getting 35 there. So this part of my equation is 35, the top part. We need to divide that 35 by what? Which is going to be what? 3, right? Because we've got 4 samples, n minus 1. So we're going to divide by 3, and then we're going to take the square root of the whole thing. So 35 divided by 3, square rooted, gives us 3.42 is our standard deviation. We need to go ahead and calculate the standard error of the mean, SEM. Remember that that's equal to the standard deviation over the square root of the sample size. So for this problem, it's going to be 3.42 divided by the square root of 4. Sample size is 4. So it's essentially 3.42 divided by 2, right? So 1.71 is our standard error of the mean. So that's for the 20 grams per liter sample. We need to do the same thing for the other samples. So let's do a little erasing here. All right, I'm going to take my formula down here for a minute. And we'll put our 40 data up here, 40 grams per liter data. The median for that 40 gram sample was 27 centimeters. We're trying to find the standard deviation and the standard error of the mean. So just like we did with the last group, we're first of all going to write down our data points, our samples, 32, 24, 29, 23. We're going to subtract the mean from each one of those. Our mean for the 40 gram sample was 27. So 32 minus 27, 5. 24 minus 27, minus 3. 29 minus 27, 2. And 23 minus 27, negative 4. Square our numbers. So 25, 9, 4, 16. And then what do we need to do? Add them up. Because remember our equation, S equals square root of xi minus x bar squared all over n minus 1. So add up that last column. Let's see, it's 2954. We're going to divide that by n minus 1, so we're going to divide it by 3. And we're going to take the square root of the whole thing. So 54 divided by 3. Take the square root, and we get 4.24 for our standard deviation. Yeah.
If, say, like on the when you calculate standard deviation, I forgot to do n minus 1 just like n. So if you did that, say like on a fair response, would they count everything after it wrong, or would they do it?
They're supposed to give you credit for parts, so you'd probably miss a couple of points, but if you did everything else right, you should get most of the points. But remember, that's one thing you need to be really careful on, because the people grading these things grade them over a period of a week, and they're reading the same thing over and over again. If yours happen to be one of the ones that get graded in the afternoon, those people are tired, and they're going to be less likely to give you those kinds of points than they are early in the morning. So overdo it. Go back and check. Make sure you get it. Let's go ahead and get our SEM here, our standard error of the mean. It's this. Remember, it's equal to standard deviation over the square root of n. So for this sample, it is 4.24 over the square root of 4. It's supposed to be square root there, I promise. So when we do that, it's going to be 4.24 divided by 2. So 2.12. All right, I'm going to back up to the problem here for just a second. Remind us what the problem was. So we calculated the mean. We calculated the standard deviation. We calculated the standard error. We did those first 3 parts. Now we got to create a graph. And it may not say a bar graph, but it tells us to create a graph that illustrates the means. If you're trying to graph means, does making a line graph, does that work? No, if you're just trying to show categories or numbers, you want to do a bar graph. So we're going to do a bar graph for the two groups. We want to have a 95% confidence interval. We'll explain that in a second, which means plus or minus 2 SEMs from the mean. So let's go back here. Let's make a little space. This is what I think they're more likely to ask you on the test. I think they'll probably give you all these numbers up here. Don't quote me on that because you never know. They always try to throw curveballs at us. But I think they're likely to give you the standard deviations and all that stuff. Now we got to graph it though. So what would be our independent variable, thing that goes on the X? Fertilizer concentration. Remember that when you're graphing, you need to make sure that you label very accurately your axis and include what? What should you include with that other than fertilizer concentration? Units. And the units, if you look back at the problem, they were given to us grams per liter. All right, then what's our dependent variable? Height. Height in centimeters. Now you need to go ahead and put some numbers on your axis and make sure that your lines are evenly spread, that the distance between every two lines is the same. So just look at your numbers. Our heights are up in the 20s, so maybe we'll go 5, 10, 15, 20, 25, 30. Go ahead and label those. Down here, our fertilizer concentrations were just 10 and 40, so maybe we'll make our lines on the x-axis be in the tens. So let's say this is 10, 20, 30, 40. Again, label those. Now we're trying to draw bar graphs. Let's do the 20 sample first. So let's go over to 20, make a bar graph that goes up to 21.5. Just draw a bar graph. I'm going to go ahead and label this point as 21.5. Now let's talk about what this 95% confidence interval thing means. What we've got to do next is use what are called error bars. And here's how an error bar is going to work. For this 20 gram per liter sample, our standard error of the mean was 1.71. So if we want to get a 95% confidence interval, we need to go up 2 times that from the mean, and we also need to go down it 2 times it from the mean. So 2 times 1.71 is 3.42. So from our mean, we need to go up 3.42. And that's going to put us at 24.92, right? Something like that. I'm going to go ahead and label that as 24.92. And then we need to go down 3.42 as well. And that puts us at 18.08. Here's what the 95% confidence interval thing means. Somewhere between the bottom of this error bar and the top of this error bar, between those two bars, there's a 95% chance that what's in between those two numbers, 18.08 and 24.92. The true mean of the whole group, not just our sample, but the population mean. That's what we mean by 95% confidence interval. To get to that, you either need to go 2 standard errors up from and down from your mean, or you could also do it in terms of standard deviation and go 2 standard deviations up from and down from the mean. That's all we got to do on the 20. Everybody okay with that? Yeah.
You always multiply 2 for the x.
If you want to get a 95% confidence interval, it's got to be 2 standard errors on either side of the mean. Okay. So if they ask you, now they might just say do one standard error on each side. They have to tell you that.
Okay.
All the questions I've seen them give you are 95% confidence interval questions, which means 2. All right, so do the same with the other one. So for our 40 group, we'll go over to 40. Our mean's 27. So let's go up to 27. Go ahead and mark this as 27. And then the standard error mean for this one was 2.12, which means we need to go up 4.24, right? So we're going to go up from here, 4.24. So we're going to go up to 31.24. And then we're going to go down 4.24. So we're going to go down to 22.76. Wait a minute, that's not right, is it? Yeah, that is right. Now, what you got to notice, and actually, let's go back to the question first. Look at the graph. The graph's finished. Let's go back and look at the question, though. The question says, based on the sample means and the SEMs, are these two populations or groups significantly different in terms of height? And justify your answer. So, the top error bar of the 20 group went up to 24. The bottom error bar of the 40 group went down to 22. That meant that in here we had a lot of what? We had a lot of overlap. Which means that the population means for these two groups might be the same thing, right? What does that mean about that extra 20 grams of fertilizer per liter? It didn't really do you any good. It wasn't worth your money. Okay? Because statistically, this mean is really not much different than this other mean. It's not significant. So our answer to that question would be, they are not very different, not statistically different, because there's a lot of overlap between the error bars. Does that make sense? Yes.
So you only look at the top and bottom?
Well, you're looking for overlap, wherever the overlap might happen. The only way, I mean, if this one's lower than this one, it's got to happen between the top of the 21 and the bottom of the 41, right?
So like which one is closer, the bottom, is that what you're saying?
Well, this one went up to 24.92. This one went down to 22.76, which means in this area, they're the same. You see what I mean? That's what I mean by overlap. So if there's any overlap between the two, if there's any points where these error bars are in the same area, that means these two things are not very different from each other. They're not statistically significantly different from each other. Does that make sense? If you know that statistic stuff, and you know how to do a chi-square problem, that's all the statistics you need to know. So I'm going to turn this off. Save it for a minute.